right, day 3 of circles. We're going to talk about tangent lines today. Tangent line, as a reminder, is a line that only touches the circle in one point. And that location where it touches the circle is called the point of tangency. So that point right there, point of tangency. And again, the line only touches the circle one time. All right, there are two main properties that we're going to cover in IM2 about tangents. The first one is the radius tangent theorem. And I don't expect you to remember that fancy name for it, but what we do expect you to know is that if we have a tangent line, right, this is a tangent line because it's touching the circle in that one spot. If we then draw a radius that goes from the center of the circle, right, radius is at the center, to that point of tangency, we always get a right angle. So again, if we have a tangent line and we draw the radius to the point of tangency, we always get 90 degrees. The angle between the tangent and a radius is 90 degrees. Which would also hold true for a diameter where it meets the point of tangency as well, right? Because the radius will be on the diameter. All right, the second theorem that we're going to use is the two tangent theorem. So now we have two different tangents, and we're not showing the whole tangent, right? I could have the whole tangent going like this, and it could keep going forever, right? It would be a line. Same thing with this tangent. It could go forever both ways. But if we just take the section from the point of tangency until it hits the other tangent. So I've got this tangent segment here, and then I have this tangent segment as well, from the point of tangency to where it intersects the other tangent. Let me go ahead and erase this just so we can see a little bit clearer. So we have two tangent segments, and if they meet in the same place, right, which any two tangents would eventually meet in the same place unless they were parallel, but anyway, when they meet in the same place, we end up getting two segments that will be congruent. So I know that the length of this segment here and the length of this segment here will be the same length. For example, if this was 10 centimeters, how long would this segment be? Yep, it's congruent, so it would be 10 centimeters. All right, those are the two tangent theorems that we're going to use. Let's do some problems. All right, first one says, determine if the line AB, or the line segment AB, right, so right here, is tangent to the circle. Well, I know that if this is going to be tangent to the circle, what angle would I get where the tangent line meets the radius? Right? I would get a right angle. So if this is a right angle, then what would be true about a squared plus b squared compared to c squared? Well, if it's a right angle, we know that a squared plus b squared will equal c squared. So I'm going to test to see if my a squared plus b squared does in fact equal c squared. If it does, I know it's a right triangle, which means that is a right angle, which means we do have a tangent line. If they do not equal each other, however, that means that this is not a 90-degree angle, so this line right here is not actually a tangent. So my two legs are going to be x, 15, and 17. Actually, hold on. Let me take a step back. Sorry. How long is the radius? I actually already know this. I don't need to try to find it. I can't find it because I don't know if it's a right angle anyway. But anyway, how long is the radius? It's 8, right? Because we have a radius right here. From the center to this point right here is 8 units long, which means this radius here is also 8 units long, because every radius of the same circle will be the same length. So now when I go to find my A, B, and C, now I actually have the numbers I need. My legs are going to be 8 and 15. So I'm going to try 8 squared plus 15 squared. And then based on this diagram, how long is my hypotenuse, or my potential hypotenuse? Right? It's going to be 9 plus 8. So I need that whole length there, which would be 17. And now I'm going to calculate, or simplify. 8 squared is 64. 15 squared is 225. 17 squared is 289. And if I add my 64 and 225, I get 289, which equals 289. So when I used the Pythagorean theorem, I got that they were equal. So if those are equal, if the two legs squared equal the hypotenuse squared, what does that tell me about the triangle? Right? It tells me it's a right triangle, which means this is in fact 90 degrees. And if that is 90 degrees, what do we now know about line AB, or this portion of the line right here? It is a tangent, because it formed 90 degrees. All right, let's try another one similar to that. We're going to determine if AB, so this segment here, we're going to see if it's tangent. So we're going to see if it forms a 90-degree angle with the radius, or in this case, the diameter. And so I need to plug it into Pythagorean theorem. If this is the right angle, then my two legs would be 9 and 13. And those would equal the hypotenuse squared. Well, the hypotenuse would have to be this side here, which it shows has a length of 15. And so go ahead and calculate that and determine, is that line a tangent? That line is not a tangent. And here's why. When we plug in, or when we simplify our Pythagorean theorem, I get 81 plus 169 equals 225. However, 81 plus 69 is actually plus 169 is actually 250, which is not equal to 225, which means Pythagorean theorem did not work, which means this is not a right angle, which means this is not a tangent line. So not a tangent. Right, but the big idea is we know that tangents will be perpendicular or form a right angle with the radius or diameter. So we're using Pythagorean theorem to check it. All right, another example here. Here's another one where they didn't give me the full length of this, but if this radius is 9, how long is this radius? Right, it is 9. And if we're looking to see if AB is a tangent, right, so right here, we're looking to see if it forms a right angle with the radius. So if it forms a right angle, we know that A squared plus B squared will equal C squared. And what are my A and B in this problem? 9 and 12. And my C would have to be this side here, which is 6 plus 9. We need both of those pieces to get a full length of 15. So I got 9 squared plus 12 squared equals 15 squared. And when we calculate that, we do get something that is true. I get 225 equals 225. And what does that tell me about line segment AB? Yes, it is a tangent. So AB is a tangent. All right, one more of those. We're really hammering this point home, right? We're looking to see if AB is a tangent again. So if it is a tangent, it'll form 90 degrees right there. This leg is 6, but on this leg, all they gave me was a radius, but I need to find the length of the entire leg. So if this radius is 4, that means this radius is also 4, which means that total length there is actually 8. So my legs are 6 and 8, and my potential hypotenuse would be 10. So 6 squared plus 8 squared equals 10 squared. And if I calculate that, you probably recognize the 6, 8, 10. That's one of our more common right triangles. I end up getting 100 equals 100, which is true, which means that AB is tangent. All right. Next problem. Find the segment length indicated. Assume that lines which appear to be tangent are tangent. All right, well, this is my line segment that appears to be tangent. And if it is tangent, I know that the radius and this line will form a right angle. All right, so this would have to be 90 degrees. So really all we've done is we've just created a Pythagorean theorem problem. All right, so lots of extra practice with Pythagorean theorem. I do need to find the length of the hypotenuse, which is not 8, right? 8 is just this section here. But I also need this section here, which I already know has a length of 12, right? Because it is just a radius, right? So that is 12. And 12 plus 8 gives me a full length of 20. All right, so I kind of made a mess out of that. Long story short, this hypotenuse is 20. All right, so I'm going to do leg squared plus leg squared equals hypotenuse squared. Subtract 144. And the square root of 256 is 16. So the length of this side right here, in order to make it a tangent, it is 16 units long. Because if it is 16 units, then Pythagorean theorem works, and that will be a right angle, which happens when we get our tangent. Okay, one more of those. If this is the part that appears to be tangent, right? And I know that in relation to the radius or diameter, we would get a 90-degree angle here. So my hypotenuse is this longest side, which is a total of 13. I'm going to do leg squared plus leg squared. Now I got to be careful here. When I do this leg, I'm finding this whole leg right here. So I'm going to call that whole leg x for now. And I'm going to borrow my calculator. 7.8 squared. Borrow my calculator. I'm going to use my calculator. 60.84. Subtract 60.84 from both sides. And I get x squared equals 108.16. And then I take the square root of that, which is 10.4. So now, here's where I have to be careful. If I put 10.4 as this length right here, that would not be correct. Because what I really found was the length of this entire leg. But what am I being asked to find? I'm only being asked to find half of it, right? Or if we use our circle terminology, I found the diameter of the circle, but I'm only being asked to find the radius. So if I know the diameter is 10.4 units long, how long will the radius be? Yes, it will be half of 10.4. So this section here is 5.2. So the radius will be 5.2 units long. Okay, now we're going to go use our second theorem, right? So our first theorem was that a tangent and a radius form a right angle. Our second theorem was that if we have a tangent, right? Here's a point of tangency. Here's another point of tangency. If we draw the two portions of those tangent lines to where they intersect, we know that this segment here and this segment here will be congruent. If they're congruent, that means they're equal to each other. So to set up this problem, I can just set those two lengths equal. I do 2x plus 2 equals x plus 8. Go ahead and get a little equation practice. What is the value of x? Well, let's check and see how you did. If we subtract x on both sides, we get x plus 2 equals 8. Subtract 2 from both sides, and x equals 6. All right. Again, if we wanted to check our answer, we could plug in 6. If I take the 6 and plug it in, 2 times 6 is 12. 12 plus 2 is 14. So that has a length of 14. And if I plug the 6 in here, 6 plus 8 is also 14. So voila, they do equal each other. X equals 6. Okay, another example. We've got this 17.9 right here. That doesn't matter. That's just a distractor. If this is 17.9, that means the other radius is 17.9. But that's not what I'm finding. I am trying to find x, which is on this tangent. It's also on this tangent. And what do I know about these two tangent segments? They are congruent. So I'm going to take 19x minus 2 and set it equal to 17x plus 2. Get the x's to the same side. Add 2 to both sides. Divide by 2. X equals 2. That was a lot of 2's. But long story short, these are equal. Set them equal, we get x equals 2. All right, a couple more of these. Now this one looks pretty intimidating, but it's the same concept that we just used. Just now we have lots of pairs of tangents that are meeting in the same place. So for example, I've got a point of tangency here and a tangent segment. I've got a point of tangency here and another tangent segment that both meet at the same place. So because those are both portions of tangents that meet at the same place, I know that this segment and this segment are congruent, which means this length is 5. And now I can do the same thing all the way around the circle. I know that these two tangent segments will be the same length, right? So this one will be the same length as this one. And I wasn't directly given that length, but I do know that this whole segment is 13. So if I take away the 5 I already have, that means that we have 8 right there. Which if this segment is 8, this segment is also 8. And then that leads me to this final set of tangents, or pair of tangent segments right here. I don't know either one, but I do know that this whole length is 14.1. So if I subtract the 8 that we already have, 14.1 minus 8 gives me 6.1. And if this segment is 6.1, what's this segment? 6.1. Now I'm going to actually read what this problem wanted me to find. This problem says, find the perimeter of the polygon. So the polygon is the shape outside of the circle in this problem, which in this case was a big triangle. And to find the perimeter means add up all of the sides. And so now that I found all of the sides, I can do this a couple ways. I can take the 13 plus the 14.1 plus this whole side, which was 11.1. Right, I can add up those three long pieces together. Or I could also do 8 plus 8 is 16. I can do 5 plus 5 is 10. And then I can do 6.1 plus 6.1 is 12.1. And if I do it that way, I get 38.1 units. If I add up 13, 14.1, and 11.1, shocker, I get 38.1. Right, so the perimeter is 38.1 units. But again, the key idea with tangents is we know that these two tangent segments that meet on the outside will be congruent. So same thing, these two tangents that meet right here will be congruent, and these two tangents that meet right here will also be congruent. Okay, so basically the same problem. Now we just have a four-sided shape, which means we have four pairs of tangents. But I know that this one and this one are the same. So if this is 10, this is 10. I know that this segment and this segment are the same, right? They're both tangents that are meeting at the same place. So if this is 7, this is 7. And then I've got 8.4, which means this one is 8.4. So now how long is this segment here? I know that the full length is 13.1. I know that this part is 8.4. So 13.1 minus 8.4 is 4.7. Which means if this tangent segment is 4.7, then the one that intersects at the same location will also be 4.7. And so now we can find the perimeter by adding up all of the parts. So 10 plus 10 is 20, plus 7 plus 7, plus 8.4 plus 8.4, plus 4.7 plus 4.7, and we get a grand total of 60.2 units. Okay, these are actually kind of fun. Maybe? Yeah, maybe. All right. Two more problems. Find the angle measure indicated. Okay, well this doesn't have anything to do with the side lengths, so I'm not worried about how long these sides are anymore. Right? I know they're the same length, but that doesn't matter for finding the angle. But if we go back to our first theorem, what do we know about a tangent and a radius? Well, we know that they form 90 degrees. Same thing with this tangent and this radius, they form 90 degrees. And a four-sided shape, such as a square or a rectangle, they always have 360 degrees. So this quadrilateral right here will have 360 degrees as well. So I can subtract 90, subtract 90, subtract 55, and I will get what is left over, which is 125. And since we're finding an angle, it's 125 degrees. So a four-sided shape will always have 360 degrees. We can use our tangents to know that those are both right angles. And then do you see any other pattern here? Do you see a quicker way that maybe we could do this? Well, if these are both 90, that means they add to 180. Okay, that's half of 360. So then what should these two add up to? Right? If these two are supplementary, then it means that these two angles would also be supplementary. So I could also just do 180 minus 55, which still gives me 125. All right, last example. We're trying to find the angle right here. Well, there's a number of ways we can do this, but one of the quicker ways to do it is I know that this angle, or sorry, this side and this side are both a radius, which means they're the same length, right? If those are both the same length, then that means that these two angles here, which are the angles that are across from those sides, they will also be the same. So if this angle up here is 24, that means this angle right here is also 24. And then I can use my triangle. I know how many degrees are in a triangle, right? 180. So if I subtract 24, that gives me that this angle here is 132 degrees. And we just said on that last problem that these two angles were supplementary, right? Because we have a right angle and a right angle, which means the 132 will be supplementary with this angle across from it. So we can do 180 minus 132, which is 48 degrees. So this is 48 degrees. Let me show you a second way that we could use, just in case that way lost you a little bit. Because it says to assume that this is a tangent, I know that this angle will be 90. Same thing over here. This side is a tangent, which means this angle will be 90. And I already know that this part of the angle is 24. So if I do 90 minus 24, I get 66, which means this angle from here to here is 66 degrees. And because we have the radii, and this is connected between the two radii, we know that these angles will actually be congruent. So that will also be 66. And then I notice I have a triangle. Triangles add to 180. So I can take the 180, subtract 66, subtract the other 66, and that leaves me with 48 degrees. All right. So kind of a lot, but again, the two key ideas, a tangent and a radius, right? That's the radius, and the tangent will always form 90 degrees. And then the second key idea is when we have these two tangent segments that meet at the same location, we know that those two segments will be the same length. All right, let's keep it rolling like circles. Hey, let me circle back to my point. I was on a tangent. Okay, see you later.